In this video, I'm going to be walking you through how to find the features of a rational function, both graphically or algebraically. The first feature I'm referring to would be a zero on a function. Conceptually, a zero is a place where the function crosses the x-axis. Mathematically, it's when the y value is equal to zero. That's why we call it a zero. In a graphic form, this is as simple as looking at the shape of the function and finding any of the x values where the function is touching that x-axis, the x-intercepts. Next, we have how do you find the zeros algebraically? Well, a rational expression is a fraction of polynomials, so you're going to set the numerator only equal to 0 and then solve for x. Sometimes that will require some factoring, maybe the quadratic formula. The next feature I'm referring to, they are called holes. More formally, you will see that they are sometimes called removable discontinuities. These are discontinuities that only occur at a very specific point in a function. To find them graphically, they're usually indicated by an open circle marked on the shape of the function. For finding them algebraically, you need to do any of the factoring that you can on the numerator and denominator. The factors that match on the numerator and denominator that can be canceled out from the expression, those can be removed from the expression. That's why we call it a removable discontinuity, and it creates that whole shape. So look for the factors on the numerator and denominator that match, and then set those factors equal to 0 and solve them. Very similar process is used for the vertical asymptotes. These are sometimes called non-removable discontinuities because there's not a way to remove that part of the rational expression. So vertical asymptotes are discontinuities caused by a vertical line on the graph. So you'll see kind of like an invisible, or sometimes it's marked with a dotted line that the function approaches but does not touch. It always gets closer and closer to it but never crosses it. For finding them graphically, look for x values that the graph is approaching but not touching. Like I said, there might be a dotted line drawn in for you, but a lot of times you're just going to have to identify it. A lot of times it goes up on one side, down on the other side to help identify those. Or it could be going up on both sides or down on both sides. For how do you find the vertical asymptotes algebraically? Similar to the whole process, you're looking for any solutions from the denominator only. So you set the factor, you get your factoring done on the numerator and denominator. You take the factors from the denominator that did not cancel out. So you do not have a matching factor for it on the numerator. And when you set those expressions equal to 0 and solve, those are the ones that create your vertical asymptotes in this case. And then the last feature we're going to talk about today, these are the horizontal asymptotes. They're similar to vertical asymptotes, but one difference on these is unlike a vertical asymptote, a graph can cross its horizontal asymptote, just as a heads up. So these kind of describe the end behavior. So if you find the limit as x approaches infinity and the limit as x approaches negative infinity, you're looking for what y values the graph is approaching on those ends. Now for doing it graphically, just find what those y values are on the opposite ends of the graph. For algebraically, I had this on a separate slide. It's a little bit more involved. We're going to be looking at a rational expression like this. Now you'll notice we only care about the leading degree in the numerator and denominator. All the other terms we can just ignore. So for example, on these problems that I have written out over here, I'm not even going to worry about the other stuff on the side. I only care about the biggest exponents on the numerator and denominator for our purposes. So there are three possible cases. If I'm noticing that n and m are the exponents on the numerator and denominator, there's the case where the exponent on the top, n, is smaller than the exponent on the bottom. Well, for example, if I have 2x squared over x cubed, whenever that situation happens, so 2 was less than 3 in this case, my horizontal asymptote is y equals 0. So this one comes up a lot. That'll occur whenever your denominator exponent is bigger than the numerator exponent. The next possible case for your exponents, what if the degrees of the expressions are equal to each other? Well, this is the most complex case. When your exponents match on top and bottom for the degree of the polynomials, we actually use the coefficients in front. So in this case, the 3 over 7 part. So my exponents were equal, and that's why this says the horizontal asymptote will be at y equals a over b, where a and b are the coefficients. So for this one, it would be 3 over 7. So the first one was y equals 0. This one's y equals 3/7. And then the last possible case is when the exponent on the top is bigger than the exponent on the bottom. For example, here my exponents are 3 and 1. So since the exponent on top was bigger than the exponent on the bottom, I don't have a horizontal asymptote at all. So that occurs quite often as well. So these are the three possible situations you have for a horizontal asymptote on the graph. Now I do have kind of a step-by-step process because you're usually going to be finding all of these features. So there's kind of an order you want to do on this. The first thing you should do is look at the degrees of the numerator and denominator to identify those horizontal asymptotes. The reason I recommend doing that first is because the rest of the steps are going to focus more on using the expression in a factored form. So if you have it in standard form multiplied out already, then go ahead and figure out which exponent is bigger, the top or the bottom, and identify where your horizontal asymptotes occur before you do anything else. Next step, factor everything. If it's not already done for you, you will need to factor that out. So once you have it factored, look for the holes next, the ones that you can remove from the expression, because if you see a factor on the top and the bottom, like x plus 2 on numerator and denominator, well then those can be canceled out. They can be removed from the expression, and any of the solutions you get from setting those factors equal to 0, those are going to be the x value locations of your holes in the graph. After you've done the removing, I would recommend setting the numerator equal to 0. So anything that hasn't been canceled from the numerator, set any of those expressions equal to 0 and solve those factors. Those will be the x-intercepts or the zeros of the function. And then lastly, whatever's left in the denominator, now set that equal to 0. Any of the factors in the denominator that have not been canceled out, solve those by setting them equal to 0, and you'll find your vertical asymptotes that way. So if you go through in this order, assuming it wasn't given to you in factored form in the first place, you'll be able to go through and then find all of your features. If it is given to you in the factored form, then you'll actually have to kind of flip the order on this. You'll need to multiply out the terms to find out what your leading terms are for the numerator and denominator to find your degrees, and then you can use that to find the horizontal asymptotes instead. So on all of the examples, I was showing you that there's both a graphical and an algebraic approach. So let me show you a graphical example first. So if I'm looking at this graph, for the horizontal asymptotes, that's where I'm looking for what does the end behavior seem to indicate. So I'm really focusing on what's happening on the left and right ends of the graph. And I noticed that for my scale, they seem to be, the arrows on the end seem to be approaching this height of y equals 1. So the graph is getting very close to 1 on the left side, and on the right side, the graph is getting very close to a height of 1. So it's going to keep getting closer and closer to it, but never hit it. So in that case, my horizontal asymptotes, they are occurring at y equals 1. I can't see the expression, but I can see that on the graph. Next, I have the holes. As I mentioned on the earlier slide, the holes are usually indicated by these large open circles. So I have 2 of them. And when we're describing the location for where something happens, generally we're focusing on the x value that it occurs at. So I have an x value of -4, and I have an x value of 0. You can have multiple holes, in which case you might want to list your answers out separated by commas, or you could write them separately as x equals -4 and separately x equals 0 for this case. Next, what are the zeros of the graph? That's where is my function actually touching the x-axis. Well, in this case, I see a dot here, and I see a dot here. Those are the places where my function is actually touching the x-axis. So my x values for this are at -1 and +1, which again, I could separate with commas, or when you have a plus or minus of the same number, a lot of times we just write that as plus or minus 1, just to kind of save writing and kind of be lazy, honestly. And then the last thing we're going to look for here is the vertical asymptotes. Sometimes they're indicated by a vertical dotted line on your graph, but in this case, what I'm noticing is it looks like my x value is avoiding x equals 2. And on this side, as I move to the right, it looks like it's shooting down and avoiding an x value of x equals 2. So it looks like I have a vertical asymptote right here. Now, as I'm looking through the rest of the graph, I see another location where that same behavior seems to be occurring. So as I go to the left on this piece, it's getting very close to x equals -2, but it's never quite hitting it. And from the other side, if I was moving to the right, I can see the same thing happening. I'm getting closer and closer to x equals -2, but the graph is shooting up, so it's avoiding that height as well. So it looks like I have 2 vertical asymptotes on this one. They seem to be occurring at x equals ±2. So the graphical approach is usually pretty straightforward and easy. Now let's look at the harder algebraic approach. So the first thing I recommended solving for is the horizontal asymptotes. So notice that I have the case where my exponents on the top and the bottom match. Both of these are x squared for my degrees. So when the exponents match, that's the middle case I gave you here. That means I need to look at the coefficients a over b. So going back to my example, my coefficients are 2 and 1. So you don't need to write 2 over 1. You would just write this as horizontal asymptotes at y equals 2. Reduce that, that fraction essentially. The next step I gave was to find the holes. So after doing horizontal asymptotes, now we're going to factor to find those holes. So for the factoring, I notice on top that there's a GCF. Both of these terms in the numerator are divisible by 2x. And if I take that out, I would be left with x minus 3. Now on the bottom, I have a trinomial, and this is the easy trinomial case because the leading coefficient is 1. So I'm going to look for 2 binomials. I know that it's got to be x times x to equal x squared. And then I need 2 numbers that multiply together to equal -3, but add together to equal -2. So in this case, I would be using -3 and +1. Because -3 times 1 equals -3, but if I added those numbers together, it would equal -2. So I have my factoring done. That was step 2. Now notice that some of the factors match on top and bottom. Specifically, I notice that I have an x minus 3 on top and bottom. So the ones that can cancel out, those are the ones that create my holes. If I set that factor equal to 0 and solve the equation, I would get x equals 3. So the ones that cancel out, those create your holes. Next, I need to find the zeros. Well, after doing my canceling, the only thing I have left on top is 2x. So I can write 2x equals 0. Okay, well, if I solve this equation, there's not really much to do here. I would divide both sides by 2, but 0 divided by 2 is still 0. So the solutions I'm getting from the numerator, those are going to create the zeros of my function. And then for finding the vertical asymptotes, now I'm going to focus on what's left in the denominator. The only thing I have left in the denominator is the x plus 1. So if I set that factor equal to 0 and solve the equation, I would subtract 1 from both sides, and I would get a vertical asymptote when x equals -1. So that's how we are able to identify all those components. It all comes from factoring the expression, canceling out what we can, and then seeing what's left on the numerator and the denominator. So the things that cancel, what's left on the numerator, and what's left on the denominator. So I hope that will be helpful on completing the assignment and understanding how to find the features of a rational expression.